Swayam Prabha. Digital India. Educated India.
So, we are ready for the next session on this printing lecture, and what we have covered in the last one is this: what is printing, how close it is from the dyeing, what are the basic steps involved like printing, drying, fixing, washing, styles of printing and methods of printing. This is what we revised. Now in the lecture 2, we will look at the essentials, ingredients of a printing paste, and one of the essential obviously is the color. How many types of colors are there, what interactions that they have, all that is important from the point of view of printing as well, like it was for dyeing, right? So, if you look at the essentials, we have colorants, which, as we said, of course, it has to be supported by what we call as a printing paste to increase the viscosity, because we want to keep everything in the boundary. It is also sometimes known as thickening or thickening agent. Okay, this is how the life goes. And of course, you will require a large number of auxiliaries to support this printing process. All right. Although we will not concentrate on auxiliaries so much, we will spend some time on colorants and just revise as to what we had probably understood before taking a printing class. So, in the auxiliaries, one of the auxiliaries we are quite familiar is called the wetting agent, right. The reason why we use a wetting agent is to reduce the surface tension, mix things properly, because most of our action is going to be aqueous, water based, and therefore what you would require is some amount of reduction in the surface tension of the systems. So, penetrations becomes easy. We are also quite sure that whatever we talk about, it is going to be a viscous paste, and a viscous paste obviously will have a difficulty in penetration. Also, we said there will be humectants. Humectants are required, again, as we said, it is a small area, small volume, concentrations are high. How do you get the water? Because we have already dried the fabric. And so, during the steaming process, during what we call as the fixation, whether it is a dry heat, superheated steam or atmospheric steam, you would get some moisture from the environment, and that moisture is going to be absorbed as such, or maybe the humectants are going to help them. The other important thing, of course, could be solvents, particularly those dyes which are not so much water soluble or their solubility is slightly less, like a dispersed dye for that matter, or wet dyes for that matter, azoics for that matter. And so, you may require additional solvents which may help it to remain in solution form. As we said, that unless and until the dye is in a molecular form, it will be very difficult for it to penetrate, diffuse into things, unless and until we are talking about pigments. Okay. Other auxiliaries would depend on what type of agent, what type of dye that you actually want to use. For example, if the dye is an acid dye, you may require acids in the printing paste. If it is, let us say, reactive dye, gets fixed in alkaline medium, so you may require alkalis. If it is actually wet dye, so you may have oxidizing agents or reducing agents as auxiliaries which we required in the whole process of printing. If you are looking at oxidation colors, you may actually have some amount of catalysts to be used, and dispersing agents would be required if we are using, let us say, a dispersed dye, because dispersed dye initially is dispersed and then of course part of it gets dissolved and then get diffused, and you get the molecular form of the dye which penetrates. Defoaming agents, foam gets generated because you have a lot of stirring being done, and it's a viscous system, and if suppose a lot of foam gets generated because you have a surface active agent which is called the wetting agent, and you must have seen whenever you do a lot of agitation in any liquid system, when there is a soap or such detergents are available, a lot of foam gets generated. It may not be the same situation here, but if the foam or the bubbles get generated and they are trapped in the paste, and when you actually do the printing, and they would burst at wrong time, and then the design will have issues. So you may be using defoaming agents. So there are many auxiliaries which are definitely required based on which type of a dye fiber system you are going to be printing. So as I said, we will spend more time on colorants because they are our mainstay. So when we say colorants, you have dyes and you have pigments. Now whether this colorant has to be used as a pigment, in that case you will be supporting its fixation by some other mechanism. But if it is considered as a dye, it must go through some dissolution process, and therefore its interaction is going to be important. Theoretically speaking, the same dye which is be used for dyeing and same dye fiber interaction which is valid for dyeing process is valid for the printing process as well. If there are different requirements, let us see if we can find them, identify what requirements are there. So a colorant is a compound which has a group which we call as a chromophore. Some of the popular names here you can see are azo, anthraquinones, keto, and others which I have not listed, you must have seen before as well. So this is the stay, the color is because of chromophore. If the chromophores are not there, the compound is not colored, and that is one of the ways we can see when you reduce, let us say, a wet dye, the chromophore is broken and the color just goes off. In most cases it becomes pale, so major color is lost. So these are the most important part of the colorant, which let us say it could be dye or a pigment. Chromogen is another supporting compound which obviously contains the chromophore. Now these type of the body, main body of the dye or a pigment is the one which holds the chromophore, but also with the fiber it must be interacting. That is, when we talk about affinity towards a fiber, then some of these things can define. If you look at the size of a direct dye, if it is large dye, most of the molecule is not a chromophore. It is just a support system. It goes inside and does not come out because it can form some bonds, let us say hydrogen bonds, with or van der Waals forces with the fiber molecule. And so this type of a thing which is called a chromogen is the body of the whole molecule which supports the chromophore but also helps in absorption. Then there are auxochromes which are smaller functional groups which can be attached at para, meta positions ortho positions of a dye molecule, they can change the tone. Let's say a blue can be a different blue, or a red can be a different red, if we keep playing around with some of these groups. This whole science is called the molecular architecture. So, a dye molecule has its own architecture, and based on these groups you can actually play around and actually synthesize a new dye molecule which may have certain interesting shade palette. And so, these oxychromes are also very important as far as, so they will be part of our dye. And yes, most of the dyes, and also whether they are through printing or dyeing process, would be applied through aquaspedium. And so these solubilizing groups are the ones which help the dye to get solubilized in water. It is not that you can solubilize them in any solvent, but we are looking at groups like SO3 Na, which is sulfonate. So they are ionic groups attached with dye molecules. So the solubility will depend on how many such molecules are attached. What is the molecular weight of the dye? If the molecular weight is very large, obviously solubilities are not going to be very high. So you have more solubilizing groups, and so you do the play around with the architecture of the dye molecule. Now this question is that what type of colorants are available? So there are large number of colorants that are available. All of them theoretically can be used for printing as well. Directs, if you look at direct dye, what is the problem with the direct dye? It was one of the easiest dye to be dyed, generally for cellulosic material, but people were not very happy with it because it was easy to dye and wash fastness was low, easy to come out of the fiber as well. It is not that every direct dye has low wash fastness, but large number of them have low wash fastness, and therefore you may not like to print with direct dyes, because printing is a costly process. You have to do a lot of exercise, and at the end of the day, if anything wrong happens, then you are not going to be very happy. So that's one dye, unless and until there are certain shades and certain types of dyes which definitely are very important and very nice, phthalocyanine based dyes for that matter. One can use direct dyes, but generally we may not. Reactive dyes, of course. I mean, reactive dyes, the name suggests that they can react with the molecules, so the wash fastness is going to be high, right? They make covalent bonds, right? And so they are good for us, definitely. So people would like to use reactive dyes. Wet and solubilized wet are two combinations which people use. For printing purposes, wet is a good color, because after you have done the whole process, it becomes insoluble, and so definitely wash fastness is high, and other fastness is also very good. Sulfur, sometimes because it's cheap, you might like to use, but it's also insoluble. But most people may not like to use sulfur as such. Sulfur is used for dyeing, but nobody can stop you for using that. Acids, metal complex, basic, that is the cationic dyes, and dispersed dyes are the ones which of course are used. And then there are pigments, organic, which are the like dyes which are insoluble. So they can be pre-synthesized molecules as a pigment which will be fixed as a pigment, or they could be generated in situ while you are actually doing this whole process, the pigment get generated. That's one. And inorganic, of course, you can use some of the inorganic compounds which give certain types of shade which may not be easily available easily synthesized in the organic, particularly in some cases the fastness properties may be also very good, and so you may like to use pigments. Let's first look at our revised, as I said, this is a revision. So, normally what would be happening is that you dissolve the dye in, let us say, water. So, we have water soluble dyes. So, in a normal case, from solution to the fiber surface, the dye goes, and then once it reaches the fiber surface, that is governed by, shall we say, affinity forces, and once they reach the surface, then the diffusion takes place depending upon the temperature, agitation and such conditions. In printing you have no scope for agitation, so you only believe that the dye definitely likes the fiber and therefore it just keeps moving in, right. This is what is going to be more important. And then of course fixation. Now fixation, if it is a reactive dye, we talk about covalent bond. If it is not a reactive dye, then it could just be van der Waals forces, hydrogen bonds and what have you. It's just like trapped inside the fiber and then doesn't have a chance to come out. So you can be trapping a big molecule inside the fiber. Once it has gone in, it has got certain kinds of interactions, and because of that it would remain within the fiber. There are some dyes like dispersed dyes and polyester. It just goes in from aqueous medium which was solution to a solid medium which is also behaves like a solvent. It can be anywhere. You see, the property of a solvent or a solution is that the concentration of a dye at any given point and any given place is same, right. That is what the solid solution means. That is the solution. That means the dye has no issue, it can go anywhere, wherever there is a space, just keeps moving, and hopefully the spaces are also uniformly distributed, and therefore dye also gets uniformly distributed. It behaves like a solution, but in a solid state. So there are some ways in which these interactions have been defined. You can do quantitative analysis also, that how much dye will go. An isotherm means that at the same temperature you are looking at how the dye moves from solution to the fiber, all right. Langmuir isotherms are the ones which are plotted at a constant temperature, like we are not talking about the dyeing starting at room temperature, raise the temperature to a certain degree, then hold it to a certain degree for a certain degree at a certain time and then drop it down, those kind of things. No? It is a constant temperature. So, at a constant temperature, at an equilibrium position, how much the dye is likely to be there in the solution, how much the dye is likely to be there on the fiber. Remember, this is an equilibrium reaction, So, this particular isotherm, Langmuir, believes that there are sites available on the fiber where the dye is going to go. That means, if the sites are not there anymore, the dye will not go, right. So, this is the thing. Like the example we said is a wool, silk, even nylon with an acid dye. So, these are the amino end groups where the dye is going to go. If the end groups are finished, the dye cannot go. This is what this particular isotherm believes. This is the postulate. So, let us say you have a saturation point, let us we call it D, or what we have called here is S, which is saturation on the fiber, and so this will move, and after some time it will not increase, right. And so the sites are finished, and therefore dyeing will not take place. And so it's got, from the kinetics you can get to this type of equation which will be valid if such interactions are there. Freundlich does not take into account as to that there are limited number of sites and therefore it cannot go. So I believe that there is an amorphous region where it will keep going. Amorphous region and the crystalline regions are interdispersed uniformly, and therefore the dye would keep on going, but the rate of diffusion would depend on how much the fiber initially has the dye and how much the solution has the dye. Therefore, the concentration of the dye in the solution and the dye on the fiber are defined by a power equation which basically would give you some curve of a parabolic type. The value of K and N would differ from fiber to fiber, like dyes which do not actually depend on any site. So, fiber has many sites or areas amorphous which is just go diffuse and enter there. So, as I said, some of the dyes will behave like this, but when the concentration become too high, the formulas may not really fit the way we want them to fit, but nevertheless mostly it is going to be true. The same power isotherm, when the value of the N becomes 1, so it just becomes dF is equal to K ds. So, it also has a saturation limit, but it goes straight as a straight line. So, based on what type of dye that we have, which does not depend on what is inside, what is outside, it just depends, it does not get governed by the inverse flow, and so the dye, as long as there is a space, it just keeps going. More is the dye in the solution, more will be the dye on the fiber in a linear way. So, when the N is equal to 1, so this formula therefore for you will be and this is the limit. After this there is no space, whatever the voids, the amorphous regions, they are also filled. Till that time it will keep doing and follow the straight line, and this is what is we call as a solid solution. So, it will just keep following, and after that it will become flat. The previous one is this one you are talking about. This actually does not believe, it believes that the rate of absorption will keep going down as the dye and the fiber keeps increasing, and because it still thinks that there will be some bonding of hydrogen bond will formation or some kind of affinity things will be there, and so rate of diffusion will keep dropping down. This one says no, if there is space it will just go without bothering as to how much dye is already present till the time when nothing is available. So, it is a question of, for example, students entering through this room from this gate, there are enough seats available. It does not matter whether 10 students are inside and the 11th will be said, let us not go because there are 10 students inside. Well, there is space, I just go, no resistance. So, it will just keep doing approximately like this. Of course, this slope of the curve is telling as to whether the dye loves the fiber more or the water more, right. This is also one of the reasons, although dispersed dye is not soluble in water, but still you dye from water. So, why do you dye from water? You could have dyed from a solvent where the dye is soluble. Why do you need to dye it from water where it is not soluble? Other dyes are water soluble, so it is very good. Here you do not want, because the water solubility was the one which was responsible initially that the new fibers like acetate fiber, polyester fiber, when they were synthesized or manufactured, those earlier dyes would not go in. And they found they are more hydrophobic, so they have to have hydrophobic type of dyes. It is not a zero solubility, but very little solubility in water. Okay. So, if suppose we say tomorrow we want to dye from a solvent where the dye is soluble and then dye the way you dye, let us say from an organic solvent like hexane, then you will find the dye goes. But the dye fiber interaction again is the same solid solution, all right. So, it will go sit in the fiber, but what you will find is the dye, because it is soluble in a solvent, it likes the solvent more. So, the partition coefficient will shift towards the solvent and not towards the fiber, and that is the reason why, although dispersed dyes are not water soluble, we still would dye from aqueous systems, right. So, it is good that more dye goes into the fiber rather than it stays in the solution. Now, this same type of colors, I am not talking about pigments at the moment, can be used for printing. How should they be different? One, many colors are being used in the same system, that of course. Mixtures are being used, yes. The fastness of the dyes in general has to be on the higher side, particularly the wash fastness should be on the higher side, okay. And therefore, it will not be so much important that you have a faster rate of reaction. What will be more important is that it is uniform and properly diffused into the fiber, and proper diffuser, at least 50% of the fabric or a fiber cross section has been taken care of. And also the difficult part, as we have said already, is the fastness of each of the mixture that you are using of the dye should be similar. It will be very difficult to be exactly same, because the molecule is different. So, theoretically you can expect that every different molecule will have a different property. But if it is in the range, we always talk about some range, acceptable limits, then it will work. So, you will have to depend a lot on the data sheet of the manufacturer and then select the mixtures, and not arbitrarily because this particular gives such a beautiful shade, let me use it. Later results will not be so nice. So, we just saying the same thing. Light fastness also, because you are going to be exposed, So, certain portions of the garment are exposed fully, certain portions of the garment are exposed less, and if the fading is not happening at the same rate, then the shade change takes place. And if the shade change takes place, then you can be quite sure people can find out there is a change of shade, it doesn't look the same, and so we would have to, because such a costly process, we would like to select such dyes where light fastness is high, of course, and also similar, so it's not easy. But you can try to find out, as I said, that how the fading takes place in your own ways. Whether if the dye fades, the fabric will get affected. A dye gets affected anyway. But do you think there are dyes which will affect the fabric? You can try and find out. There are some wear dyes which were stopped, the manufacture was stopped at some stage. Whether the substrate affects the fading, whether the substrate affects the fading. So, this is an important thing. One of the interesting case is there, and you can appreciate in the light fastnesses, you absorbing certain amount of energy. This energy is absorbed by the molecule which is called the dye. It does in any way absorbs, otherwise nothing will be seen. But you have UV light also, but not just the visible. So, if you absorb certain energy and that energy changes the molecule, damages the molecule, then obviously fading takes place. If suppose the energy, instead of the molecule actually changing itself, passes on this energy to the fiber, because the linkages are such that can actually transfer the energy. So, fiber, if suppose some damage takes place, will take place, but fiber being a large volume, large mass, it may be smaller. The dye is a small molecule just sitting somewhere on the surface and trying to do whatever, particularly surface. The fading will be felt on the surface. The dye which is inside the fiber deep is not even visible. So, you will not see whether it is faded or not, and most probably it is not even faded, right. So, we are looking at surfaces. Printing is based absolutely on surface, surface interaction with our own eyes, and that is how the printing takes place. And so, one case, for example, the cationic dyes, you can dye them on cotton also through a mordant. You can similarly print also. You can have those same dyes on acrylic fibers. Okay. Now, generally it was felt, and it may have been, you may remember also, the light fastness of the basic dyes on cotton were found to be relatively poor compared to even direct dyes, light fastness we are talking about. But the same dye, if applied on acrylic fiber, shows higher dye, higher light fastness, because you make an ionic bond there. It is relatively more easily able to transfer the energy to the fiber. A dye feels safe, and so fiber dye interaction can actually play some role in the fastness, defining the fastness, light fastness also. Wash fastness you understand very easily. There is a bond made, less bonding, more bonding, covalent bonding, ionic bonding. They will all play a wash fastness role in determining what is the wash fastness. But light fastness also gets affected. You can read more about it. The wash fastness, of course, is important. Higher the wash fastness, better it is as far as the printing is concerned. But you would be also very much interested in staining resistance. Staining resistance is important, because when you wash, some of the dye solution during washing will flow over the areas where you do not want it to be there. And you must remember, stain is generally difficult to remove, easy to happen, because the equilibrium is in the favor of the staining, because the color is more in the solution, let us say, and there is no color on the fiber. Although temperatures of course are different, you are not giving the right pH, you are not giving catalysts, anything else, therefore we do not expect so much to happen, but stain is a stain. and that's what you have to worry about. And so one would like to have such dyes which do not stain easily. You will have to wash sometimes also. No? When you wash the same garment, it's got portions which are white, portions which are light, and so anytime the dye can get exchanged. So the staining is an important part. You will like to choose. Perspiration, fastness, of course, are important because, and rubbing as well. So if you have dyes which are not soluble, which have not reacted, which after process would be available in particles, even small, or dimers, trimers, and larger things, which become insolubilized after the process is over, they may have a tendency to get out also, because they may be on the surface. Let us say azoic, okay? They may remain on surface, and so the problem. Or the indigo, for example, the denim. So affinity is less, does not penetrate more, but you like it anyway, and so rubbing fastness. Unless and until there is a fashion, it may not be very good. In the case of dispersed dyes, you should be bothered about sublimation fastness as well. You see, for the same reasons, the sublimation fastness is not very high. The wash fastness may be good because dispersed dyes are not water soluble. And let us say you have done the printing with dispersed dyes on nylon, which you can do. When you store also at temperatures which are not very high, but let us say go up to 50 degrees in some cases, you may see sublimation very low, but it is there. It is good enough to stain, and that's it. Your print is over. The problem is not that how much dye you have lost. You have lost the whole fabric or a garment which you may have paid for. So this is the general question is that do the dyes have all these fastness very good? Well, they are not. Sometimes the shade, you have to compromise, because the shade desires that such dyes must be used, otherwise you will not obtain, then you have to compromise. But everything not being same and not in your favor, still you have to work around. If you have the choice, you better exercise the choice. That's how we would like to call. So let us say wet dyes, they are generally used for printing without any doubt. Okay. Why? They have all kinds of fastness which are very good. Very important from the printing point of view. You look at the wash fastness, you look at light fastness, all kinds of fastness. They are very nice dyes, but they are expensive. So you can appreciate anything which does everything right will be expensive. Not just as a dye, but also the whole process. You have reduction, oxidation, all that has to be done. So they are good for printing, cost is high, so no problem, you should be able to use them. Which type of a fabric can be printed with wet dyes? Just give me some answer. What type of a fiber fabric? Cellulosic. Okay, very good. So this type of a dye, the way it is, can be used for cellulosic, cotton, viscose, etc. If suppose somebody says, I want to use it for wool and silk, is the dye has a problem with the wool and silk? So what is the problem? Alkali and the process is a problem, right? If suppose you can solve this problem, then you should be able to dye. And that is why people made something called a solubilized wet dye. The same dye has been changed that you have now groups attached, they make the dye soluble. So these are sulfuric esters and sodium salts of sulfuric acid, because every time you make these compounds, you got to make a salt so that they remain ionic and so water soluble. So, it's the same dye as before, just that the structure has changed. So, because of this particular group that has been added, you are now here, this is the change from the previous dye, and suddenly this dye can be used on any fiber which is hydrophilic. Okay. So, you can go on silk, you can go on cotton, you can go on rayon, you can print on nylon, no issues. But why should you? That is a separate question. Cost is very high. Fastness, you would like to have any questions on the fastness? Do you think the fastness will be different? It should not be. It is the same molecule. If the molecule, because at the end of the day, this will become the same dye after final little oxidation cycle. It will be the same dye. And so, this is what we call as engineering a molecule to your own advantage. But cost is high, and of course, the palettes that are available, color palettes that are available, palette that is available is not as large, as wide as the wet dye, but cost is quite prohibitive. But for printing purposes, if you really want it, they are there. So, all substrate can be used. Reactive dyes became very popular, right, and also for dyeing as well as for printing, because you have, let us say, something called this. So, you have a dye and a reactive group. Of course, there would be a bridging group and everything else. There is a chromophore, you can see this also will behave like one. And so, reactive dyes, everybody loves them. So, we spend some time here before we, they are water soluble, no issues on that, because they have various kinds of groups, which sulfonic acid groups that are attached. So, what is the process? The process will be, first you dissolve, then you make a paste. After making a paste, you do whatever, and then it must bond. So, you must provide a condition at a right time. If you provide the condition of fixation at the wrong time, then you get a wrong results. So, let us say it requires alkaline condition. The alkaline condition must be provided at the time of fixation. If suppose the alkaline condition, right alkaline condition is provided in the paste itself, a paste is stored for a long time, it is not made every minute and not easy to make also, it requires energy and effort. And therefore, what we will do? You will provide alkaline conditions at the right time. This particular dye is called a dichlorotriazenyl system, sometimes known as the M type of reactive dye. This is not used for printing generally. It is too reactive, lot of wrong things will happen, right thing will happen later. So, you want to create a condition, let us say it will fix at 60 to 80 degrees centigrade, then at room temperature it will not fix. So, whatever kind of material that you have, whatever anything else that you have, there will nothing will be happening at that time, it will happen at the time. So, you might prefer this dye, where one of the chlorine has been substituted by an amine. So, reactivity has gone down, and time required, temperature required will be high, but for printing it is a good idea. Saving time is not a good idea. So, these are some of the reactive groups. As we said, the reactivity should be less, fastness obviously will be high, and this would, two things which we quickly talk about. The fastness, if the reactive dye has reacted with fiber, it makes covalent bond, so should not have any fastness issue as far as the wash fastness is concerned. But if it has not reacted, then you have a problem. So, if you are looking at a cotton, where does it react? To the hydroxyl groups. Whenever there is a water, there is a hydroxyl group. So, it will react with water also. If it reacts with water, those, let us say 1 chlorine in a monochlorotriazine type of a dye was there, this will react with water, a dye will not react, it will just be there. You wash it, it will come out. So, fastness property would depend on how have you actually proceeded, whether most of the dye has reacted or most of the dye has not reacted or reacted somewhere else or in some other form, then you have a problem. Then this question of substantivity versus reactivity. So, you want it reactive, again moderate, like you said, I do not want a dichloro. Substantivity also moderate, that if at all it has hydrolyzed and is available when I do good amount of washing, it should come out, so that the customer does not complain. It should come out while you are processing. If it is high substantive dye, then it will have different ways of bonding other than the covalent bonding also, and it will stay and keep coming out every time you wash. And so, the wash fastness sometimes reported may not be 5, it will be less than 5. How can you have? Reactive dye less than 5 means what? It means you have done bad job, dye has reacted with water and is available on the fiber, and so the new molecules will have moderate reactivity and moderate substantivity, so that can come out. Which substrates can be printed with? Little louder. Which substrate? Yeah? Cellulose. Of course, they were designed for them, but wool, silk can be, and you do not really have to go to the alkaline pH also. They can react, and so hydrolyzed dye issues will also not be faced with silk and wool. So, they are one of the best actually in India also. A large amount of silk printing is done by reactive dyes, and so they actually show better fastness. They can react with free amino groups, end groups that are present in approximately neutral medium. You can do an acidic medium, but neutral is the best. And so, no hydrolyzed dye, because hydrolyzed dye is formed in alkaline medium. I think today we will like to stop here, and next time when we meet, take it further. Right? Thank you.